Welcome back to the drawing board with me, Stephen Lloyd, and in keeping with this time of year, we're doing a bit of a seasonal special talking about snow loads. One of the biggest factors that affects your snow loads is whereabouts in the world you are. In our case, in the UK, simplified this map to three general areas. Down in the southwest, tend to use the value of 0.4 kilonewtons per square metre. It means there's a little smattering of snow on top of a piece of ground. 0.4 to 0.6 around the middle of the country. This 0.6 threshold is quite important. You'll hear a lot of structural engineers talking about service loads, imposed loads on a building, on a roof for access and such. And these tend to be around about 0.6 kilonewtons per square metre. So if you're already accounting for that kind of value, there's no point accounting for snow loads as well. You tend to have already taken them into account. Further up north in Scotland, particularly in the Highlands, you're dealing with values greater than 0.6, and snow loads may be the dominant factor in the design of a roof. This really only accounts for snow on the ground, and then you take into account other factors that modify those loads, which we'll talk about on the other side of the board. Another factor is the return period you're looking at. Generally speaking, for Eurocodes, you look at a return period or a reference period of 50 years. Now, this doesn't mean that the storm will only come once every 50 years. It's a probabilistic approach that the chance of that storm happening or that snow event happening in 1 year for a 50-year reference period is 1/50th. For a 20-year, it's slightly more, it's 1/20th, it's 0.05, and for a 100-year, it's much less. You can modify these loads. If you're looking at a short period of time, the chance of having a big snow event is smaller, so you can reduce those loads down to about 80%. If you're looking at a longer period, for instance, if it was a monumental structure or a big civils project, you might extend that reference period and you need to increase the size of those loads. The chances of you getting a big snowstorm in a longer period of time is greater. So we talked about this not being one storm that comes every 15 years, rather it's a 1 in 50 chance of it occurring in 1 year. This led me on to Bernoulli Trials, which was really just an excuse for me to draw a nice Christmas tree on this seasonal board here. Bernoulli Trials can help you work out the probability of an event occurring a set number of times in a given number of trials. In this case, we're looking at what is the chance of having 0 storm events, 1 storm event, or more than that in a 50-year period. We know that the chance of it happening in 1 year is 1 in 50, and we can use Bernoulli's little formula here to work it out. I will put a transcript underneath this video showing the workings out, but for now, if you just take it for granted that the probability of a 1 in 50-year storm happening never in that 50-year period is about 1/3. The chance of it happening just once, the time that you'd expect it to happen just once, is also about 1/3. And actually, there's about a 25% chance of it happening 2 or more times. Got a little distribution here. So if you design something and you expect it to last until that big storm comes and it falls down, chances are only 1/3 of those are actually going to last the 50 years that you've designed them for, which is quite an interesting thing to think about. So we talked about snow on the ground and how often that snow arrives. Snow on the roof now, we have to modify those values to take into account certain properties of the roof itself. The shape of it, the roughness, and also the thermal properties. If you have a roof that's not very insulating over a warm building, chances are a lot of that snow is going to melt away before it ever builds up. Properties of the location are also important, not the geography, but the sort of microclimate properties. Other buildings nearby, trees, are you on top of a hill, are you on the side of a hill? Things that affect small local areas that could make it easier or harder for snow to build up and get snowdrifts. So how do you take those properties into account? Now come over to these diagrams here. The steeper the roof of a building is, the less likely it is for snow to build up on it. You can see in this diagram here we have a slightly steeper side to it, which has less snow built up on it, and a less steep side. Now there is an exception to that, and we'll go through these 3 cases here. The first case is what's shown in the diagram. A smaller amount of load on the steep side, a bigger amount of load on the shallow side. But what if there's wind that's drifting that snow? If there's a side that is facing the wind and the wind's coming from this direction, even though it's sloped more, the chances are more snow will get built up on it because the wind's blowing against the slope. In that case, you get a distribution that looks more like the second case. And on the opposite side, if the wind's blowing this way, chances are you'll get an even smaller amount of snow on that side, and so you can reduce that and you end up with the third case. In the case of roofs with just one slope or with a dual pitch, it's not that difficult. It's when you start to get things like you see factory units that have the numerous slopes to them that end up with these channels in between. Where you have the channels in between, where you have a valley, snow can build up quite substantially when there's wind and can drift in and leave you with a large force in the middle there. These are the occasions where, even coming back to this map, further down here, if you ever have large buildings with valleys in the roof, you really should be thinking about snow loads, because they're the times when unexpected volumes can build up. In this case, there are equations in Eurocode that tell you just how much snow might build up, but as a general rule, as you go deeper into the valley, more and more snow will be there, and as you emerge from the valley, you'll return back to a similar value that was in these cases here on these slopes. There is one further rule you have to look at as well. Where you have a roof adjacent to another, but at a lower level. Not only do you have to take into account the snow drifting into the corner here, but you have to take into account anything sliding off the higher roof and landing on top. So anybody who's got a conservatory that's butted up to the end wall of your house, you're going to have to be very careful this winter, make sure no snow comes sliding off your roof. The top roof, very similar to what we just looked at here. The bottom roof, very similar to this valley here in working out the drift, and then a little bit extra that's determined by just how high above that roof is there and how long and how far away from the roof you're extending. I've not gone into any specifics, but this is a seasonal episode, but hopefully that's given you a bit of an appreciation of snow loading. Please enjoy your holidays, and I'll see you in the new year and come back to the drawing board.